This here is promethium, the second lightest element for which there is no stable isotope. What do we have here? 1 milliliter of promethium chloride PmCl3 solution with an activity of approximately 2 gigabecquerel, so about 0.058 milligrams of promethium. Unfortunately, this concentration is not sufficient to detect the beautiful pink color of promethium 3+ ions through the UV vis or even the naked eye. A lot of information about promethium. What are we going to discuss today? The production of promethium and naturally occurring promethium, decay data of promethium-147, and briefly the applications in nuclear batteries. So promethium is radioactive and therefore it took some time to discover it. It was discovered as a fission product of uranium. When uranium-235 undergoes fission, the fission yield of the 147 isobar is approximately 2.2%. Yes, promethium-147 is not the most long-lived isotope, but it's the one that's produced the most in the context of nuclear fission. So when dealing with radionuclides, even with the transuranium ones, it's not always about the most long-lived, but rather what's the easiest one to produce with a half-life suitable for practical applications. In this case, it's the 147. The other isotopes are also produced in nuclear fission, but the most long-lived promethium-145 is only formed as a direct fission product. It's worth noting that the fission products come from a neutron-rich nucleus, uranium-235. This means that fission products are more likely to be formed with a neutron excess and then decay via beta-, ultimately forming promethium-147. Let's say in one fission, praseodymium-147 is produced as a fission product. This one can decay. In the next fission, neodymium-147 is formed. It can also decay to the promethium isotope. If any other isobar is produced as a fission product, for example the 146, and praseodymium-146 is formed, it decays into neodymium-146, which is stable. This means, in the case of promethium-146, it needs to be a precise match when it comes to fission. In the first case, theoretically the entire 147 isobar with every nuclide will form promethium-147, whereas in all the other isobars it needs to be a direct hit in order to form promethium. The 149 is also open, but after a month there will be nothing left from the promethium. Okay, sure, promethium can be also artificially produced by neutron or proton irradiation of neodymium. So that's why the focus is usually on the 147. I will come back to that in the gamma spectrum later. Naturally occurring promethium. Yes, I've mentioned it is produced by the fission of uranium. If you look at the chart of nuclides, you'll see that for naturally occurring uranium, there's also a decay mode with a probability of less than 5% called spontaneous fission. And when it undergoes spontaneous fission, promethium can also be formed. Yes, uranium-235 is also possible, but there is simply an extremely large amount of uranium-238. So much so that due to this spontaneous fission, about a little over half a kilogram of promethium naturally occurs in the world. Neutron-induced fission by cosmic radiation cannot be ruled out, but it's so unlikely that it's practically negligible. And now it gets even more interesting. Europium-151 is listed as a stable isotope in most charts of nuclide. Well, here we have a paper, and their results are as follows. Europium-151 has a half-life in the order of 10 to the power of 18 years. To measure this, calcium fluoride europium-doped scintillation crystals were used. You can read more details in the paper, linked in the description. And this Europium-151 can decay, producing promethium, and it's responsible for about 12 grams of naturally occurring promethium. So much for that. Let's move on onto the decay data. First, the gamma spectrum. Promethium-147 is quite challenging in this regard, with a probability of the 121 kiloelectron-volt line of 0.003%. You can't see that. But what you can see are the lines of promethium-146 and 145 in our sample. As I've mentioned, all promethium is produced from fission products, and the other isotopes can be formed as well. Isotopically pure promethium would be just unnecessarily expensive. expensive. The low energy range is broadened because I've measured it through the lead vessel. Additional data, half-life 2.6 years, it's a beta-minus emitter with a maximum energy of 224 kiloelectron-volts and an average of just 61 kiloelectron-volts. It decays into the primordial radionuclide samarium-147, and promethium-147 has a specific activity of 34,000 gigabecquerels per gram. Since it's a UG nucleus, 61 protons, 86 neutrons, it has a half-integer nuclear spin, which in this case is plus 7/2, resulting in the preferred decay state of samarium-147 with a nuclear spin of minus 7/2, being populated through the decay. Don't worry about it, I'll explain this in more detail in the future. Nuclear batteries, they work by sandwiching promethium oxide, PM2O3, between two semiconductor photodiodes. Important, even though promethium undergoes beta-minus decay, it emits electrons, but these are not the same electrons that provide the current. Instead, the decay generates an electrical signal in the photodiodes, which will then produce our electric current. Lifespan, it's about 1.6 years, and a battery with a total size of 5 cubic centimeters would generate a few milliwatts of power. The great thing is that the nuclear batteries do not rely on chemical processes and therefore are almost temperature independent, which is quite good when it comes to very low temperature application. More on that in the description. Now we know more about promethium than we did at the start of the video, hopefully. A special thanks goes to the working group of Analytics and Fundamental Nuclear Chemistry from Dr. Erik Strupp and the Division of Nuclear Chemistry at the University of Cologne, and to my Patreons. With that being said, goodbye!